Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. And the problem is given as you are given a number and you have to find all the prime factors of that number. In case you do not know about the prime factors, let me tell you what does it mean. So these are all the factors of 12 because 12 can be divided by 3, 4 and 6. And out of these factors, 2 and 3 are prime numbers. So we can say that 2 and 3 are prime factors of 12. Now if we write all the prime factors of 12, it comes out to be 2, 2 and 3. Why? Because if we multiply 2 into 3, we get 12. In case of 13, the prime factors is only 1 because 13 is itself a prime number and the prime factors of any prime number is going to be only 1. Similarly, in case of 540, the prime factors of 540 are going to be 2, 2, 3, 3 and 5. It means 540 is divided by 2 times, 3 by 3 times and 5 by 1 time. And in this example, all of these are prime factors of the corresponding number. Now let's pause this video for a while and think about a solution to solve this problem. Now let's see this implementation. And this is the simplest implementation to solve this problem. So we have a function and this function is taking n as input and we are simply running a loop from 2 to less than equal to n, right? Inside of this loop, we are simply checking if I is prime or not. Because we only interested in prime factors, that's why we are checking if a number is prime or not. If number is prime, then we are simply storing the number in variable x and we start our while loop. And in while loop, we are checking if n is divisible by x. If it is divisible by x, we simply print on the screen and then we increment the x by multiplying it with I. So basically what this function is doing, it simply start a loop from 2 to less than equal to n, and in each iteration it tries to take out all the multiples of 2 from a given number. For example, in case of 12, it starts with 2 and it takes out all the multiple of 2. It means it checks if 12 is divisible by 2, then it prints 2. In next iteration, it checks. In next iteration, the x become 4. It checks if 4 is divisible by 2, then again it prints 2. And it continues this process until we get all the multiples of 2. And once all the multiple of 2 comes out, the inner loop gets terminated and the control goes back to the parent loop. Okay. So in next iteration, the I becomes 3 and the while loop simply checks if n is divisible by 3 or not. This time the 12 is divisible by 3. So it gets printed. So 3 gets printed on the screen. In next iteration, the x become 9 and now 12 is not divisible by 9. So this loop, inner loop gets terminated and the control goes back to the outer loop. Now in next iteration, the value of I becomes 4 and it checks if 4 is prime or not. 4 is not prime. So it continues to next iteration. In next iteration, I becomes 5. It checks if 5 is prime or not. 5 is prime. But while loop is not going to run because 12 is not divisible by 5. So this process continues and the for loop reaches to I equal to 12. So this is how we print all the prime factors of 12. So the idea is simple. Just run a loop from 2 to n and for each I take out all the multiple of 2 from the number n. Okay, so far so clear. Let's talk about the time complexity of this function. So if I ask how many times this loop is going to run, our for loop is running from 2 to n. Okay. So the time complexity is n, and inside this loop our is prime is taking n unit of time and the while loop is taking log n time. Why log n time? Because in each iteration we are multiplying x by I. So whenever we have this type of scenarios, the loop generally takes log n time. So in total we have n multiplied by n log n, right? So the time complexity comes out to be upper bound of big O of n log n. Now can we optimize this code little bit? Yes, I think there is a room for improvement. So let's see how we can implement this code further. So here we have some observations to be made. And what is that? See, the observation is whenever we have divisors of a number, that divisors always appear in pairs. So for example, in case of 20, the divisors are 120 2 10 and 5 4. Because if we multiply 1 by 20, we get 20. If we multiply 2 by 10, we get 20. And also if we multiply 4 by 5, we get 20. And this happens with 30 also. 1 into 30 is 30, 2 into 15 is also 30, so on and so forth. And if you look at this example closely, you can see that the one divisor is always smaller than the next one. Here 1 is smaller than 20, 2 is smaller than 10, 4 is smaller than 5, so on and so forth. So we can do some observation here. Let's say we have a pair xy, and when we multiply this x and y, we get n, right? Because when we multiply 2 into 5, we get n, right? And in this observation, we saw that our x is less than equal to y. And we also know that if we multiply x with x, it means if we multiply 2 by 2, it becomes 4, and 4 is always going to be less than equal to 20, correct? So by this, we can conclude that x into x is always less than equal to n, and we get our x as less than equal to n. So it means if the value of x is less than equal to n, then definitely the value of y is always greater than square root of n. Simple. Let's see here. See, the first value is 2. It means this value is always less than equal to square root of 20. And the second value is always going to be greater than square root of 20. So far so clear. So after analyzing this, we got some hint that in previous example, we are running our loop from 2 to n. But after looking at this observation, we can conclude that we can run our loop from 2 to square root of n, and in between 2 to square root of n, we get our first factor. So let's implement this observation into our code and see the next implementation. So in this implementation, I have simply replaced the n with the square root of n, and else we are doing the same thing. And one more thing to notice here, that I am checking that if n is greater than 1, just print n on the screen. So I will explain this in a bit. And here I am dividing n by I every time. So what we are doing basically here, we take out multiple of 2 and then we divide the n by 2 so that we get the remaining number, right? So let's say in case of 21, the square root of 21 is 4. So this loop runs from 2 to 4. In first iteration, I is equal to 2. We check if 21 is divisible by 2. This condition becomes false. So the loop continues to the next iteration. In next iteration, the value of I becomes 3. In while loop, it checks if 21 is divisible by 3 or not. This time it is divisible. So the 3 gets printed on the screen. And at the same time, we divide the n by I. So now our value of n becomes 7, right? Now in next iteration, the while loop checks if 7 is divisible by 3 or not. This time it is not divisible. So the while loop gets terminated and the control goes back to the outer loop. So the next iteration of in the next iteration of the outer loop, the I becomes 4. And so the 7 is not divisible by 4. That's why our while loop is not going to run this time. So this time the 5 is not less than square root of n. So the loop gets terminated. But we only have 3 on the screen. We still have one factor left, right? That is why I have written this condition here, that if n is greater than 1, just print the value of n on the screen. And why this is happening? Because there might be possible that one factor is greater than square root of n. We have seen here that if one value is smaller than n, then definitely one value is always going to be greater than square root of n. That's why we are simply checking if any value is left or not. If any value is left, then just simply print that on the screen, right? Now let's talk about the time complexity of this function. So this function simply runs from 2 to square root of n. So how many times the loop runs? Square root of n times. So simply the time complexity of this function comes out to be upper bound of square root of n, and that is big O of square root of n. Okay, so far so clear. Still, I would say that we are still wasting a lot of iteration. We can still have room for some improvements, right? So let's see how we can further optimize this function. Now again, we have some observations to be made. So the observation is, in previous example, we are running loop from 2 to square root of n, and we are checking each number like 2, 3, 4, 5, 6, and all of these. But we are not considering that if a number is divisible by 4, then definitely it is divisible by 2, right? Because the 4 is a multiple of 2, right? Because 2 into 2 is equal to 4. And similarly, if a number is divisible by 6, it means it is divisible by 2 also. And if a number is divisible by 9, then it means it is divisible by 3, right? Because 9 is a multiple of 3. Then why we need to check for 4, 6 and 9? We can simply use 2 and 3 to check all these numbers, right? So I mean to say, if I check any number for 2, then I don't need to check that number for 4, 6, 8, because that number is going to be multiple of 2 and we have already checked it. And similarly, if we check a number for 3, then we do not need to check for 9 and 15 because that number is already multiple of 3, right? So we simply ignore checking the multiple of 2's like 4, 6, 8, 10, 12, 14, 16, 18 and 20, right? And if we check for 3, and if we are checking for 3, then we do not need to check for the multiple of 3, that is 9, 15 and so on and so forth. So this way we drastically reduce the iteration in our code. So now what we do, we simply have to handle 2 and 3 explicitly, right? And by doing this, we do not need to check for the multiple of 2 and 3. So now let's implement this observation in our code and see how we can optimize the code better. So this is our final implementation, and this is far most the best implementation so far. Okay, so what we are doing in this function, first of all, in first line we are checking if n is equal to 1, then simply returns, right? Then in first loop we are explicitly handling all the cases for 2. So it means we are taking out all the multiple of 2 in this while loop. And in next if statement, we are explicitly handling the value for 3. So we are taking all the multiples of 3 out of the n. So we are taking all the multiple of 3 out of n. Simple. And along with this, we are simply dividing n by 2 here, and we are simply dividing n by 3 here, so that we get the remaining number. And after both the if statement, we are running a loop from 5 to square root of n. Now this time we are not running a loop from 2 to square root of n. We are running a loop from 5 to square root of n. Why? Because we have already handled 4, right? Because 4 is a multiple of 2, so we do not need to check for 4 now. For your information, I would say that I have discussed all this concept in previous video. The name of that video is prime numbers. So if you have not watched that video, then I would highly recommend to watch that video. Come back here and continue watching this video. Okay. So in for loop, we have 2 while loops. In first while loop, we are checking if n is divisible by I. If it is divisible, print it on the screen and divide n by I. In next while loop, we are checking if n is divisible by I plus 2. If it is, then print it on the screen and divide number by I plus 2. And at the last, I am checking if n is greater than 3. If it is, then simply print it on the screen. This condition is for the corner case, right? So I will show you in a bit. So let's dry run this program. Let's say the value of n is 540. So the square root of 540 is 23. So the execution begins from the first line. The value of n is 540. So we continue to our first loop. So we continue to our first if condition. The value of n is 540 and it is divisible by 2. So we get into this if statement. And then the value and the while loop also checks if n is divisible by 2. And this time it is. So it takes out all the multiple of 2 from 540 and at the same time divide the n by 2 again and again until we get all the factors of 2. So this way 2 gets printed on the screen 2 times and the value of n reduces to 135. Now the same thing happens with the second if statement also. Here we are handling for 3. So we take out all the multiple of 3 from 135 and all these multiples gets printed on the screen. And our n reduces to 5 this time. So we get 2 times 2 on the screen, 3 times 3 on the screen, right? Now our execution reaches here and it's time for for loop to get executed. So for loop starts executing. The value of I is 5. It checks the value of 5 is less than square root of n and the condition becomes false. because 5 is not less than square root of 5. So we hit our corner case, and in this case the value of n is greater than 3. So the 5 gets printed on the screen. So this is how all the prime factors of 540 gets printed on the screen. That is 2 times 2, 3 times 3 and 1 times 5. Let's see with another input. So let's say the input we are using this time is 21. The square root of 21 is 4. So our execution begins from here. Our first if statement checks if 21 is divisible by 2. The condition becomes false and the execution moves on. The execution comes to the second if statement. It also checks. This time it is divisible by 3. So the while loop gets executed. The while loops take out all the multiple of 3 from 21 and the n reduces to 7. So when condition becomes false, we get out of this while loop and from this if statement. Now the execution reaches here at for loop. The for loop starts running. The value of I is 5 and 5 is less than it, and it checks if 5 is less than square root of n, and the square root of 7 is something, but the 5 is not less than the square root of 7. So this loop is not going to work. We simply get here and it checks if the value of n is greater than 3 or not, and it is. So the 7 gets printed on the screen. So this is how the prime factors of 21 gets printed on the screen. Now let's talk about the time complexity of this function. So how many times our loop is running? So in case of prime number, so if we pass prime number to this function, let's say 7, so the if statement is not going to run, this if statement also not going to run, and then the for statement runs from 5 to square root of n, and inside for statement the while loop is also not going to work, and this while loop is also not going to work because the number is prime, right? So we simply hit this condition and the number gets printed on the screen, but the for loop runs from 5 to square root of n. So in case of prime number, the time complexity of this function comes out to be square root of n. So let's say what happens in case of composite number. Let's say if I pass 20 to this function, our if statement is going to run. It takes out all the multiple of 2, then it takes out all the multiple of 3 if exist, then for loop is also going to run, and this time as the number is composite, so maybe the inner while loop is also going to work. So this time the number is composite, so it may be possible that both the while loop is also going to work. As we are reducing n by I, so the value of n is reducing drastically. So this for loop is not going to run from 5 to square root of n because we are reducing n again and again. So it's going to run less than square root of n times in case of composite numbers. So the overall time complexity of this function comes out to be upper bound of square root of n, that is big of square root of n. Alright, so I hope now you have clear understanding about how to print all the prime factors of a number. So this is it for this video. Thanks for watching. See you in the next video.